Okay, let's get started. So course announcements, problem set 4 is out. It is due November 6th, which is, again, a Friday, end of the day Friday. This is just for cat people. I'm definitely a dog person, so I'm just not, I had to grit my teeth a little bit not to put a puppy, but this is a really cute cat. Any questions? We'll come back to puppies. Okay. There are questions about the problems, but yeah, if you have questions about the problem set, please post that in the Slack, either on the problem set channel or to me directly. Right. Okay, let's continue with quicksort. So quicksort was another divide and conquer approach. I think I said dynamic programming last time. Divide and conquer is a better way to describe this. We'll get to dynamic programming approaches later on. So divide and conquer just basically means you divide up a big problem into a bunch of small problems. We did this with merge sort. We also are doing it with quicksort. So take an element X from somewhere in the list, go through the list one by one and pivot using X. That means putting everything lower than X in some list L1 and putting anything higher than X in L2. And remember, we're assuming that our list doesn't have any two things that are exactly the same, though it's easy to generalize it to that. And then sort L1 and L2 recursively using the same approach. And then combine L1, X, and L2 in that order. So that's the quicksort sorting algorithm. So last time we were considering if we pick the pivot randomly, and again, we're going to be considering if we pick the pivot randomly, the best case time is if we happen to pick the pivot that exactly divides the list in two. Since we don't know what the numbers are in the list ahead of time, we don't know how to pick that pivot. It's not like we could say, it's not like we could just determine what the midpoint of the list is and then just use that as the pivot. We don't know what the numbers are in the list. We don't know what the midpoint is, and determining that would take some time too. So the best case time is going to be on the order of n log n, so theta of n log n. Remember, that means asymptotically bounded above and below by a constant times n log n. And the worst case time is theta of n squared. And that's if we pick the pivot right at the end. So we're basically not getting any kind of divide and conquer from quicksort at all. Are there any questions before we go a bit further? So what do we think is the average case time? Like expected. It's not really the average over instances. It's more the average over, in this case, how you pick the pivot. At least what do we know about the expected, the average case time, given that we know the best case and the worst case? Yeah, it's somewhere between the two. It is somewhere between n log n and n squared. Okay, so it's probably, maybe it's either n log n or n squared. If it were literally the average of the two, then what would it be? Yeah, it would be n squared because the n squared would just dominate. Okay, so let's see. So what is going into the time of this algorithm? Well, the time of the algorithm is dictated by the number of comparisons between two elements to see which is bigger, right? Because that is the actual meat of the thing. Once we've determined what's in L1 and what's in L2, then we just put all those things together. But we have to determine what is in L1 and what is in L2. And then sorting L1 is itself doing a bunch of comparisons between elements. This is the key to any one of these sorting algorithms we've looked at, considering two elements and seeing which one of them is bigger. Okay. So suppose the list contains the numbers like z1 through zn in some order. Now, let's consider, we're trying to work out this number of comparisons between two elements. And a good way to do something like this is to write x as the sum of indicator variables. Right? X is the indicator variable to see whether zi and zj are compared. So the indicator variable just means it's 1 if they are, it's 0 if they're not. And you see why x is equal to the sum of xij. So why does this help us? What technique can we use? What thing can we use? Linearity of expectation. Yes. So we've written x, which is the thing we want to get the expected value of, as a sum of some things. So we can just express x as the expectation of x as the sum of the expectations of the individual xij. And since these are binary valued variables, they're 1 or 0, it is just, each of these is just the probability that these things actually get compared. That's just what the expected value is for something that is either 1 or 0. It's the probability that it's 1. Okay. So now we want to work out the probability that we are going to compare zi and zj. At any point in the algorithm. So let's think about when zi and zj get compared. So here is an example. We have the list 526143. We've picked as a pivot number 4. In this case, the numbers happen to be the numbers 1 through 6, but they could be any numbers. It could be like, this could be 10 or 1,000 or 1,000,000. Okay. So if we pick the pivot 4, we've divided the list into the things before 4 and the things after 4. So in this case, 4 is going to be compared with everything, and 3 and 5 will never be compared, no matter how we do this sorting, because they're in different lists. Right? We can generalize this argument. If we pick a pivot between zi and zj, then we will have divided the list into a list of things before that pivot and a list of things after that pivot. And so zi and zj will never be compared. Like if zi was 3 here and zj was 5, we'd be good. They'd never be compared. However, if zi or zj were 4, then no matter what the other one is, they will be compared. So basically what we see here is zi and zj are compared if and only if we pick one of them as the pivot before we pick any of the other numbers between them. So if you imagine we pick one of the other numbers between them before we pick them as a pivot, well, that means we've divided the list into 2 sublists, and zi is on one side and zj is on the other side, and they're never going to be compared. But if we pick zi or zj as a pivot before that, then we're going to have to compare zi and zj. Or questions about this? So what's the probability that we pick zi or zj as a pivot before picking any of the numbers between them, strictly between them? Remember that all the numbers overall there are n numbers. They're like z1, z2, z3, all the way up to zn. First of all, how many numbers are there between zi and zj? For everyone writing zj minus zi, careful with the indices. Yeah, so the total number of numbers between zi and zj inclusive is j minus I plus 1. So we could look at what the probability we're looking for, probability of comparing zi and zj, is just the probability of picking zi first plus the probability of picking zj first. And any of these numbers can be picked first with equal probability because we're just picking pivots randomly. So probability we pick zi first is 1 over j minus I plus 1. Probability we pick zj first is 1 over j minus I plus 1. So the overall probability is going to be 2 over j minus I plus 1. And this sort of makes sense, right? If we picked two numbers that are like right at the start and right at the end, it's going to be less likely we're going to compare them because probably we're going to pick something in the middle first. So if this is big, we're less likely to compare them. If they're right next to each other, we're more likely to compare them. Or we have to compare them, actually. Okay. So now our total expected value is just summing this thing, j minus I plus 1. And it gets a little bit thorny. I can just pull out the 2, first of all. And just write this as like 1 over 1 plus 1 over 2 plus all the way, how high could this be? Well, j could be all the way up at n. So it could be n minus I plus 1. Okay. But this, here, I'm just going to do an upper bound here. So this is less than or equal to if we went all the way up from 1 over 1 to 1 over n. And then this is equal to O of n log n. Why is that equal to O of n log n? Oh yeah, we did that last class. 1 over 1 plus 1 over 2 all the way up to 1 over n. So the harmonic series, this is called, is actually theta of log n. Why is this big O instead of theta? Why am I writing big O instead of theta? Yeah, because this less than or equal to, I mean, technically this is equal to theta of n log n, but the overall thing, since we have a less than or equal to, we don't know how much less than or equal to it is, right? Like this thing over here could theoretically, the less than means I have to make it into an O of instead of a theta of. And it means we only have one side of the bound. Okay, so E of x is equal to O of n log n. Cool. So can it be less than n log n? Can it be can it be little o of n log n? We like thetas. What, can we make it be theta n log n? We don't want it to be just less than or equal to n log n. This is the expected time of the whole algorithm. Is it possible that the algorithm runs in just order of n time? Oh yeah, we have the best case. The best case is n log n. So since the best case is theta of n log n, the average running time is not just O of n log n, it's actually theta of n log n. Because we're not going to be able to do better than the best case. Okay, other questions? There's a question about, what if we pick an element to the left of I or the right of j? So back in this previous slide, here, if we picked an element that was less than zi or greater than zj, it wouldn't have helped us. Basically, that is like is saying, are we going to compare 2 and 3? Well, if we pick 4 as a pivot, that doesn't help us work out if we're going to compare 2 and 3, because if we pick 4 as a pivot, 2 and 3 are still in the same list. We're going to work out if we need to compare 2 and 3 if we have we're going to compare 2 and 3 if we pick 2 or 3 as a pivot before we pick something between them. So if there were 2.5 in this list, then if we picked 2.5 as a pivot, we would immediately have broken this list without comparing 2 and 3. But the only way that you can prevent two things from being compared is if you take a pivot between them. And between them, not in the sense of like where in the list, but like something that is literally less than one and greater than the other. Good question. Are there more questions? I realize this argument was a little bit, like, takes a bit to wrap your head around. Yeah, so there was a question about the harmonic series. It's not exactly equal to log n. So again, this is equal to log n. If you multiply by n, it becomes n log n. So why is this order of log n? Well, what we actually wrote was that I'm sorry, I didn't put this on the slides. I should have done that. What we wrote was that if you take 1 over 1 plus 1 over 2 all the way up to 1 over n minus 1, that is greater than or equal to log n. And if you take 1/2 plus 1/3 all the way up to 1 over n, then that is less than or equal to log n. And so it's pretty easy to show that the first one means that 1 over 1 plus 1 over 2, I'm writing this in the chat, plus 1 over n is greater than or equal to log n plus 1. And the second one shows that it is less than or equal to log of n plus 1. And since log of n plus 1 and log of n plus 1 are both theta of log n, we're done. So it's upper bounded by theta log n and lower bounded by theta log n. Yeah, so they're not exactly equal, but they're equal. They're not just equal really by a multiplicative constant, they're almost equal by an additive constant. Like they're never actually, they never differ by more than like 1 in any direction. It's pretty cool. Cool. Yeah, these are a really good approximation. It's like surprisingly good. Okay, so let's now move on. So we talked about trees, and let's just talk about rooted trees. So this is actually how a lot of computer scientists think of trees, but since I'm a mathematician by training, I think of trees without roots. So yeah, I realize that doesn't really make sense from like a botanical point of view. So a rooted tree is a tree where one node is identified as the root. It can just be any node. For any node, there's just one path to the root since it's a tree. There aren't any cycles. Remember, that's the definition of a tree. There are no cycles. So there's a unique path to the root. And that means that every node has a depth, which is the number of edges between it and the root. So this is a good example where you have like, you typically will write the root sort of, it's actually really weird why people designed it this way, but like a lot of the time you will see trees written with the root at the top instead of at the bottom. It's weird. Somebody didn't know what a tree was. So the root is at the top and the leaves are at the bottom, and the root is at depth 0. And then this is all the things at depth 1, and this is all the things at depth 2, and so on. You can just sort of order them like this. And then you can say that things have parents. So every node of depth greater than 0 has a parent, which is its unique neighbor at depth d minus 1. There's exactly one thing it is adjacent to from the previous depth, and that's its parent. So then there are also children. So every node has exactly one parent, unless it's the root node, in which case it doesn't have any parents. If W is the parent of V, then V is said to be a child of W. So this is this green node, which is a leaf, is a child of the white node here. And the white node is a child of the black node. Okay. Questions about terminology? Okay. Binary trees are rooted trees where every node has at most 2 children, which are designated left and right children often. Often binary trees are used to store data in their nodes. We can talk about binary search trees later, but we're not going to do that today. This is an example of binary tree. 2 children, 2 children, 2 children. Here, this is just, this doesn't have it. I guess this was you don't have to have every node have 2 children unless it's a leaf. You could get rid of this node, this 0, and it still would be binary. Okay. What can the maximum depth be for a binary tree with n nodes? You're all right. It's not n, it's n minus 1. It could just be a path with each node being the parent of the next. So it could have depth n. It could just be all the way up to the root. It's a tree with like just one leaf at the end. Yeah, so sorry, this should be n minus 1. What is the minimum depth? Log n, order of log n. The tree can be perfectly balanced with 2 nodes of depth 1, 4 of depth 2, and so on. Let's just quickly work out why the depth is log n here. So in this case, if the depth is d, we have the total number of nodes being the maximum number of nodes, I guess, being n is 1 plus 2, so 2 at depth 1, 4 at depth 2, all the way up to 2 to the d possible nodes at depth d. And this sum, remember we had this nice formula, 1 plus x all the way up to x to the d is equal to x to the d plus 1 minus 1 over x minus 1. Just sending that to the chat. So that was just a factorization. So that means we can write this as 2 to the d plus 1 minus 1 over 2 minus 1. 2 to the d plus 1 minus 1. This is a good thing to remember, that if you add up all of the powers of 2, you get 1 less than the next power of 2. So like 1 plus 2 plus 4 is equal to 1 less than 8. And this is the reason why binary representations of numbers work, for what it's worth. 1 plus 2 plus 4 is 7. And if 1 plus 2 plus 4 plus 8 is 15, so 1 less than 16. Okay. So the exact expression should be log n plus 1 minus 1 is a question. You need to deal with like floor functions, because not everything's an integer unless it's a power of 2. But yeah, this is just so we don't have to worry about whether it's a power of 2 or not. Theta of log n. But yeah, it's like it could vary by like by a factor of 2 here actually, because if you had basically like oh, sorry. Yeah, if it could vary by like, sorry, it could vary by like 1. So like it could be like a log n plus 1 ish. Yeah. So yeah, there's like a floor or ceiling function depending on how you want to write it. I'm not going to worry about that. Questions? Heaps. So that's what we're going to be talking about mostly today. So a max heap is a binary tree in which the key stored in any node is greater than the value stored by both its children. A min heap is just the same, just with min instead of max. We're going to assume that heaps are max heaps here, but the same logic would just apply exactly to min heaps. In general, you could imagine another heap property where a node has this heap property with respect to both of its children. Here, the heap property is greater than, but it could also be less than. It could also be something else. So here's an example of a heap. You can see that 8 is greater than 2 and 4, 7 is greater than 1, 14 is greater than 8 and 7. 16 is greater than 14 and 10. And 10 is greater than 9 and 3. But it doesn't matter which way these two are arranged. So for example, the lesser child, as it were, could be on the right or it could be on the left. So right here, 2 is less than 4, but here 7 is less than 8. So we don't care about that. We just care that the parent is always greater in value than the kids, as it were. Don't actually use kids for children. Always say children. Yeah. So what are these other numbers hanging around here? Well, this is just sort of making it easier to implement a heap in a computer. So we also assume that in a heap, I guess I should have said, each row, set of nodes of a single depth. We'll get to these little numbers in a moment. We also assume that in a heap, each row, set of nodes of a single depth. That's what a row is. So like this is a row, this with 1 node. This is a row with 2 nodes. This is a row with 4 nodes, and this is a row with 3 nodes. We assume that each row is full, so it has like the maximum possible number of nodes, except possibly the last one. So here, this has 4, which is the max. This one has 3. The max will be 8, because you can imagine 8 nodes of depth 3. But we're going to assume that everything's full except possibly the last one. So the depth in particular, that means the depth is like theta of log n. We don't have one of these super unbalanced binary trees, which is just like a path. And we're also going to assume the last node has all its nodes as far left as possible, just easy by swapping left and right. Like if this, we could swap this so that this one was hanging out over here on the right-hand side, but let's just move everything over to the left. Okay. Now this is like, there's one particular way. Suppose we have any in this case, how many numbers are there? There are 10 numbers. There's exactly one way to write the structure of the heap with 10 numbers. It has to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then the values in it could be arranged in several different ways. Like we could have swapped 3 and 9, and that would give us a different configuration here. And we could have done various other things. Like we could have even swapped like 4 and 3, and that would have given us a different way to write this in a heap. Okay, are there any questions for the moment? Okay. So what are all these little numbers? Here nodes have a key, which is a value stored in them, and also an index, which is starting from the root and counting across each row in turn. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the reason why this is a nice way to index things and why there's this other thing written here is indexing makes it really easy to move about in the tree with just bitwise operations. So how do you get from a node to its left child? With the indexes, the indices. Yep, just double it. Just double the index. You get from 3 to 6 here, from 5 to 10. That's how you get to the left child. And the reason for that is just because every one of the nodes that had a smaller index must have 2 children. And so the child of your node, so say the child of 3, has to come after the children of all of the previous nodes, basically. Are there questions? Okay. And then for the right child, you just double the index and add 1, because that's just moving 1 more. Okay. So making a heap. How do we make a heap? I'm going to make a heap from a list. Well, as we saw, there is exactly one shape for the heap. So we can start by throwing the numbers into the right shape in some order. We need to reorder them. So each parent is larger than its child, or its children, though. We don't necessarily have the heap property just by throwing things into the right shape. So how can we do that? Let's start making this happen with the bottom row. So the bottom row doesn't have any children. So we're already good there. There's no problem with a parent not being larger than its children because there are no children. Now, what about the next row up? If any number is less than one of its children, we can swap it with the larger one of its children. And a similar process for rows higher up, and we'll see an example in a moment. And just keep on swapping with the children. So let's assume that the nodes at depth greater than k are sorted correctly. And now we're going to look at depth k. if the node is smaller than one of its children, we're going to swap it with that child. Or sorry, swap it with the larger of the children. And then when where the key is now, we swap it again if necessary. And we continue swapping until either the max property is satisfied or we've reached a leaf node. So for example, here we're trying to make this node satisfy the heap property. And we're assuming that everything below it, and we're assuming the nodes at depth greater than k are already sorted correctly. So everything below it has already been sorted correctly. But here, 4 might be less than one of its children. So here we're going to swap it with the bigger one of its children. So 14 now goes up here. And we're over here now. 14 is up here. 4 is now over here. But we need to keep on doing this. So we need to swap 4, in this case, with the only one of its children, which is bigger than it, which is 8. And so then we have 4. Now it's 14, 8, and 4. And now we're down at the bottom, and it's good. And you can see why this works, because in each case, we are ensuring that the heap property works at that node because we've explicitly picked the larger one of the children, which is definitely larger than the other child. And we're only doing this if it's larger than the original parent. So it's going to be larger than both the children. So 14 has to be larger than its children now. And because of the heap property, because the heap property was satisfied before, we know 14 was larger than 8 here. And so 14 is still going to be larger than 8 once we've moved 8 up here. And so we're never going to violate the heap property. Are there questions? OK. So we can now do this to order the entire heap. The way in which we're going to do that is we're going to take the bottom row, and the bottom row is already done. And now we're going to go through the next to bottom row. And so 10 and 9 were really easy because they were leaf nodes. They didn't have any children. 16, we need to consider if we need to swap it. But it's greater than its children already, so we're fine. 2, no, we need to swap it with something. We need to swap it with the child that is greater. So we swap it with 14. OK, now we go to the next node, which is 3. We're going backwards through the heap here. We did this. Now we go to 3. Do we need to swap it? Yes, we need to swap it. We need to swap it with 10. So 10 goes up here, 3 goes down there, and that's it. We don't have to swap it anymore. 1, we need to swap it down because it's less than both its children. So we swap 1 with 16 because that's the bigger one, and then we swap 1 again with 7 because once 1 is here, it's still bigger than its child. So then we end up with this. And then finally, we need to swap out the root. And the root is greater than both its children. And so we swap it with the larger of the children, which is 16. And then we swap. We have 4 here and 16 up here. Didn't show quite all the steps. And then we need to swap 4. So we swap 4 with 14. And then we swap 4 with 8. And so we have 4, 8, 14, 16 being the full path. And basically, it just moved 4 down the path to the end. Sort of swapped the whole thing. Questions? So this is just doing this whole sort of swapping thing for each of the nodes in the heap. OK. How long does this take? So the question, do we not care whether the right child is greater than the left child? Correct. We do not care whether the right child is greater than or equal to the left child. This is not a search tree. This is a heap. Good question. So how long does this take? Okay, so there's fairly good agreement that we are doing this in n log n time because each of the swaps goes down depth log n most, and we're doing it n times. It's actually not true. Or it is O of log n, sorry, O of n log n, but it is even better than that. So we have to fix every node in the heap. How long does it take to fix a node at depth k? So we're fixing the bottom row first, and that took 0 time because there were no swaps necessary. Depth 1 above the maximum depth is going to take 1 swap. If you're 2 above the maximum depth, or 2 less than the maximum depth, then it takes 2 swaps, potentially. 3 above, it takes 3 swaps, and so on. So we have to swap a node at depth k up to d minus k times if d is the maximum depth. How many nodes are there at depth k? It might not be completely 2 to the k, but yeah, up to 2 to the k at least. Yeah, and you don't care about the last row anyway, because that's 0. But yeah, up to 2 to the k nodes at depth k. The total number of moves is less than or equal to d minus k, which is how many swaps it takes to correct a node at depth k, times the number of times you have to do that at depth k. That's 2 to the k. D minus k times 2 to the k. So what is this? We're summing this from k equals 0, which is the root node, which there's only one root node, but you're going to have to swap it a lot to get it all the way down. And you're going all the way down to depth d, where there are a lot of nodes, but you're not going to have to swap them many times. And this is sort of the key to why there's a savings in making a heap, because you have to do a lot of swaps, but only for the nodes which are higher up the heap. And the nodes which are higher up the heap, there aren't that many of them. Okay, so let's try writing this out. Here, there are d minus k copies of 2 to the k. So for example, if k equals 0, there are d copies of 2 to the 0. So it's 1, 1, 1. These are all the d copies of 1. There are d minus 1 copies of 2, d minus 2 copies of 4, and so on. There's only 1 copy of 2 to the d minus 1. We agree that this is the same. What can we do with this? What can we do with each one of these terms? Silence. Yeah, whenever you see the sum of like 1 plus 2 plus 4, there's a simple way to write that. 1 plus 2, all the powers of 2 up to a certain power. There's a simple way to write that. Yeah, it's the same formula that we saw before. Each of these becomes a power of 2 minus 1. So this is 2 minus 1, this is 4 minus 1, this is 8 minus 1. This is all the way up to 2 to the d minus 1. and just moving all this stuff around, there were d of these, so it's minus d, and it's 2 plus 4 plus 8 all the way up to 2 to the d minus d. And then we use it again. And this is not quite as nice as this, because it's missing the 1 in front. So it's actually, this is 2 to the d plus 1 minus 2 instead of 2 to the d plus 1 minus 1, because it's also missing the 1. It's 2 to the d plus 1 minus 2 minus d. And why are we happy about this? Can we relate this back to the number of the size of the heap overall, like n? Yeah, d is log n, or order of log n. So order of 2 to the d, so it's order of n. So it actually just takes linear time to make a heap, which is kind of surprising. Okay. Questions? Okay. So now we're going to see priority queues. And we're not going to be able to finish priority queues, but just like a little bit of this. And we'll finish it up next time. So a priority queue is a data structure that allows you to perform a number of different operations. First of all, you can insert a new key into the data structure. You can find the maximum of the data structure, of the priority queue. You can extract the maximum. That's actually like removing it, so it's no longer in your queue. And you can increase any particular key, which is taking the element at index I and increasing it to the value x, assuming that it was smaller than x before. A min priority queue is the same thing, except it allows you to insert, take the minimum, extract the minimum, and decrease a key. And so, yeah, I mean, the idea of maximum or minimum is that sort of they're prioritized by this. Like a priority queue, if it's a max priority queue, it's really good at finding maxima. If it's a min priority queue, it's really good at finding minima. There's a question about the previous proof. The number of swaps is different from the number of comparisons. Which is greater? The number of swaps and the number of comparisons, they're related at most by a constant, because the number of comparisons you're having to do is just like twice the number of swaps, because you're having to compare it to its two children. Good question. So yeah, there's a constant factor in there. Okay, so yeah, a min priority queue and a max priority queue are these different data structures optimized for sort of finding minima and finding maxima. And priority queues are super useful across different algorithms. We're going to see next time how they are useful in Dijkstra's algorithm. And in particular, we're going to see how a max heap can be used to implement a max priority queue. And a min heap can be used to implement a min priority queue. They're not going to prove that's just exactly the same thing, only with min instead of max everywhere. And we will prove that all of these operations, in fact, do work out next time. Thank you for coming. I will stick around for any questions.